1 minute. Okay. Are you guys ready?
Yeah.
Okay. So we do it this way. So we divide it into two. I take a break in the middle because I need to work out something. Is that fine? Okay. So let's go till maybe 45 minutes, and we go for a short break and we continue. Because there's something I should have worked out, but I was too busy to work it out. Okay. So fortunately, this is the most have you started? Okay, so fortunately, this is the most interesting part of the talk, and unfortunately, not so many people are around. So I guess they would have time to watch this. So we discussed about these two integrals the other time, and these are really nice integrals. The first one is a very standard integral, while the second one is a popular integral for a complex analysis course, and we were able to solve this by differentiation, right? Okay, and I promised to send the solution. Okay, I would do that maybe after this talk. I would do that, and yeah. We started with Wallis integral here, or let's say the integral that induces Wallis product. And we discussed these slides up to the 17th slide. Okay, just as a briefing, this is the integral that gives the area of the quarter circle. And we know what the area of the quarter circle is, pi over 4. And here we have a quote from George Andrews, Richard Oskey, and Ranjan Roy, which says, over 70 years before Euler, Wallis in 1656 tried to compute the quarter circle integral to reach a formula for pi. But since he could only undo integrals of this form, which are very elementary forms, he used the value of the quarter circle integral and some audacious guesswork to propose what became Wallis's product. And, this is a quote from 3 famous experts in special functions. Okay. So here is just a discussion on the parameterization of that integral. So when you make this substitution, the integral reduces to this. And we know what this is, pi over 4 from the previous slide. And this is what the quarter circle looks like. And this is the area beneath that quarter circle. So it's just this part of the circle, pi over 4.
Something happened to the scaling.
Huh? To the scaling?
It's to the scaling, yeah.
How?
Yeah, it has to be like exactly the quarter circle.
Yeah, because right now it's a bit looking like an egg.
Ah,
Yeah,
wow, interesting. Let me see.
Did you draw it in MATLAB?
I would say,
from MATLAB, sorry.
no, Mathematica. Well, I think probably because of the square root, it looks like this. Yeah, it does look a little bit like an arc.
You just probably didn't set scaling for the axis, but
like the same, because like 0.2 on y is definitely smaller than 0.2 on x, like looking
Yes.
wise.
yes.
Probably, you might be right, but this was drawn with Mathematica.
It's not essential.
Yeah. Okay, so one could consider through 2 symmetric families, and yeah, Alexander asked the question how these 2 integrals are the same, and we were able to justify that, right? By the substitution pi over 2 minus theta. And that's the symmetry of the sine and cosine So by that you have that these two integrals are the same, which means any which integral you pick to consider, you would end up with the same result. That's the meaning. And we can just work with In and remember that I2 is J2, which is pi over 4. So you could try to work with the cosine one, but I would be working with the sine one. But they are the same. We have these two first values. I0 is 1, so I0 is pi over 2 and I1 is 1. I'm sorry. And by integration by parts, we have a reduction formula for In. We have this reduction formula, maybe not this, but the next slide. In the next slide. This is the reduction formula. And to get this, you just replace this cosine squared theta with 1 minus sine squared theta, right? And then you get this reduction formula. And from this reduction formula, you get two chains. You get these two chains. And we explained how we could get this recursively, right? So you could just remember that In is a simple product of rational factors times either I0 equals pi over 2 or I1 equals 1. For theta between 0 and pi over 2, we have that sine theta is between 0 and 1, and we have this inequality. From this inequality, we have this inequality for the two families. So I'm just giving a summary of what we did the other time until we get to slide 17. So these have been discussed. So we could just divide by I to n plus 1, and this is a typo. I corrected it in the previous version, but this is the slide with pauses, and it's not yet reflected. But never mind. This is just subscript. They are the same with what I intend in the previous line, okay? So you could just divide by I sub 2n plus 1, and you would have this result. And from here, this fraction comes from dividing the product in the previous slide. You just get this fraction. So what can you observe from here? You could take the limit as n goes to infinity. If you do that, you have that 2n plus 1 over 2n goes to 1. And by squeeze theorem, you have that this limit is just 1, right? Okay. From that limit, we could construct Wallace's product by just dividing these two things. And noting this fact. So we get Wallace's product by just dividing these two products. Next, I gave a summary of what we just did. So you could start with IM, or you could start with JM if you wanted. You could derive recurrences for I2n and I2n plus 1 just from the recurrence relation for IN. And these recurrence relations are referred to as reduction formulas in a standard calculus course. Could use the inequality for this, apply squeezed theorem to get that ratio going to 1, and combine explicit products for I2n and I2n plus 1 to yield Wallace's classical product for pi. And there's also a Wikipedia page on this. You could check it out. A useful observation. Okay, when we make the substitution t equals x squared, we get this integral. And now the authors that we mentioned before, George Andrews, Richard Askey, and Ranjan Roy, mentioned something on Wallace's integral, which was why I started this particular session with Wallace's integral. So this is a quote from the three authors. They said, of course, Wallace did not write his product as a limit or use the gamma function. Still, his result may have led Euler to consider the relation between the gamma function and integrals of this form, the integral of x to the power of p times 1 minus x to the power of q on 0 to 1, where p and q are not necessarily integers. And now we are getting to the beta function proper. Starting with the beta integral. Okay, and I explained that these integrals become template integrals. And one of the cleanest templates is the beta integral. So many integrals are just the beta integral in disguise. Some by differentiation, some by some substitution, and we would discuss this in this slide. We would be discussing this in this slide. Okay, what can you observe about this beta integral? One, it depends on two real parameters, x and y, which is very obvious. Two, the integrand is a simple product of powers on the fixed interval 0, 1. And three, in many problems, a messy integral becomes this shape after what I put in quotes, good substitutions, depending on what you mean by that. It could be a nice substitution, it could be a terrible one, but good substitutions. So the goal of this talk is to recognize when a complicated integral is just a beta integral in disguise. Basic identities we will use. Before using beta xy as a template, we record a few identities that are easy to verify and will be used repeatedly. We proved this the other time, if you could recall. The first one is on symmetry. Beta xy is beta yx. And we showed this by this substitution, if you could recall, by making the substitution u equals 1 minus t. You would be able to observe that beta xy is beta yx. Secondly, we have the edge cases. By the edge cases, I mean what happens when one variable is when one variable is 1 and the other is kept fixed. Okay? Or rather, when one variable is 1 and the other is just itself, we just leave it the way it is. So this can be proven elementarily, right? This is just a very simple integral. You could make a substitution if you want, maybe a u equals 1 minus t and just integrate. You would just have a minus behind that and put the boundary values or the integration limits. So, and you have this for beta x1 to be this. So beta x1 is just 1 over x as well. So these are the edge cases, and they are the very simple special cases of the beta integral. The next one is the structural relation. You have this very nice formula for the beta integral. Gamma x, gamma y over gamma x plus y is just the beta integral. And with this, your life has been made very easy. You would be able to solve an integral in just, 3 minutes, depending. So, okay. Now, I believe this is where we begin. Recognizing the beta shape. So this is the target form. This form is built entirely from powers of t and 1 minus t. Many integrals can be rearranged into this shape with a suitable substitution. The interval is fixed, 0 to 1. Only exponents change. The structure stays simple. Once the integrand matches this pattern, the result becomes beta x, y. So what this means is this form is built entirely from powers of t and 1 minus t. You could rearrange some integrals in this form. For instance, if you have, just think about it. Maybe you have 4t, maybe to the power 9, and you have a 6 minus 6t squared, maybe, if you want. Y minus 1, Yeah, maybe you put a, I don't know, a 7 if you want, to t. You could just bring out the 6, make some substitution for t, maybe some t squared equals p, and you know, you just arrive at this form. So that's what I mean by the third line. Once the integrand matches this pattern, the result becomes beta xy. So it becomes of that form. So common root 2, 0, 1. So many integrals become beta shaped after a standard change of variable. Before we start this part of the talk, I think it's preferable that we do some demonstrations. Okay? So I wouldn't just be talking. So I would give you an example of what we are talking about. So if you look at this integral, for instance, okay, maybe let's look at this, dx over x cubed plus 1 over x cubed. So this is one integral here that we would try to evaluate. We would return to this talk after evaluating this integral, okay? Now, yeah, let's start immediately. So the first thing to do would be to simplify this, which would be by multiplying by x cubed over x cubed. And if we do this, we're gonna have this x cubed dx over x to the 6 plus 1. Agreed? Good. So the next thing we would do would be to make the substitution b equals x cubed. Okay, no. This is x6 at the denominator, so we would respect the denominator more, and we would be making this substitution. So I make my life very easy. When I write this, I just write x in terms of p immediately for differentiation purposes. So this is x in terms of p, so I just differentiate very easily. So dx would be 1 over 6 p2, 1 over 6 minus 1 dp. Very simple. Let's just call this integral I, as we usually do. So we would have I to be, well, the integration limits would stay the same because when x goes to infinity, p goes to infinity. When x is 0, p is 0. So we would have this, and p now is this. Okay, so what do we write for x cubed? X cubed would just be p to the half. That would be x cubed, right? P to the half. So this would be p to the half times p to the 1 over 6 minus 1. Okay? 1 over 6 behind this over p plus 1. Okay? And this would be 1 over 6. So we could just do half plus 1 over 6. And that would be 6, 3 plus 1, 4 over 6. Right? 4 over 6 is 2 over 3. Right? Minus 1 over p plus 1. We forgot the dp. This is dp. So with the beta integral, I would just write this b 2 over 3, 1 over 3. Okay? And this is just gamma 2 over 3, gamma 1 over 3. Okay, we forgot the 1 over 6 behind it, 1 over 6 behind it. And this is just what? This is 1 over 6 times pi over sine pi over 6. Oh no. Pi over 3. But I could take a minute to cross-check what I did for possible errors. Okay. Yeah, I like cross-checking what I did. Okay. I like cross-checking what I do. So if you multiply by x cubed, this is x cubed, this is x6 plus 1. We make p to x's, then x is p to 1 over 6, and x cubed would be p to the half, and dx would be 1 over 6, p to the 1 over 6 minus 1. Half plus 1 over 6 is 2 over 3, okay? And we have 2 over 3 minus 1. And this is just this here. Made 2 over 3, 1 over 3. Okay, everything is fine. So this would be the result, pi over sine this. So what is sine pi over 3? That's sine 60 degrees over 2. Good. So the result should be pi over 6 times root 3 over 2. So this would be pi over 3 root 3. So I could take a moment to verify this answer, because I just thought of this integral randomly. Let me see.
Could you turn off the projector, because on the...
Huh?
Could you turn off the projector while you're checking, so that on the video...
Oh, okay, yeah, I would do that, I would do that.
No, because of the projector, it's too light.
I see. Okay, to turn off the projector. Okay. Okay, that's correct. Okay, I should use a handkerchief. Okay, so I could show you the check I just did. Let's give it an escape here. Okay, let's check it out. Okay, so to check this out, we just go to Wolfram. Okay, where is this? Wolfram alpha. Okay. And we just press integrate x to the 3. Okay, now I cannot find exponent on this German keyboard. Okay.
If you think I know, I don't.
Okay. Okay, you know. Okay, come help me. I always get confused with the keyboard. It should be here. Oh, thank you. You saved the day.
Yeah.
So this is 1 plus, okay, I've seen plus, x to the 6, okay, from 0 to infinity. And, okay, I am looking for y
It's,
beneath. Okay, so we see this, right? The, yeah, and that's our result here. So, and then you could check out the integral and see how complicated it is. So, you don't need to do this to get pi over 3 root 3. So you get it now.
Clever.
So with the beta integral, life becomes easy. Okay, we could go back to the slides and now continue the talk. So, yeah. Okay, let's wipe the board. Okay, before that, I would give another integral, but it would take me 2 minutes or 3 minutes. I don't know. I'm not with a timer, but let's just see one here. So if we have this integral, okay, could you give me a number, Alexander? 7. Nice. You like primes? Let's, with the cos. And you? 3. You all like primes. Okay, so I would compute this, okay? So the result would just be be 7 plus 1 over 2, 3 plus 1 over 2. Okay? And that would be half b 4, this is 2. Okay? And this would be half gamma 4, gamma 2 over gamma 6. This is 1 factorial. Okay? I will just write half, for the sake of explanation, 1 factorial over this 5 factorial. So this is going to be half times 5 times 4. And this is going to be 1 over 40. So that's the value of the integral. Okay? 1 over 40. So I did not need a reduction formula, you know, complicated steps. You don't need that, obviously. So it's as simple as this. And we could try to verify, because it's important we also verify. Okay. So we want to integrate sine x to the what? X to the 7. Oh shit. Oh no. The keyboard is messing with me again. 7 and cos 3x from 0 to pi over 2. Okay. Okay, 1 over 40. So we are correct again. Yeah. Good. And you can see what the integrand is. So sorry, this is what the indefinite integral rather. This is what it is. But to get here, you would have to do a lot of work. But I didn't do a lot of work and I just got the value of the integral. So that's the point. Okay, so back to the talk. Yeah. Okay, so yeah, from 0 to infinity, we make, so if you check an integral and the integral is on 0 to infinity, you try to make this substitution, okay? So these are just some tricks you could try. You try to make this substitution to convert to 0 to 1. Ideally, you don't need to, right? You don't need to if it's of this form, okay? But for the sake of the talk, I would be showing you how these conversions work. From 0 to infinity, you could get it back to 0 to 1, and then you just see it in the beta xy form. If it's on 0 to pi over 2, you make this substitution, okay? And if it's already on 0 to 1, you just rewrite it so that it becomes a power of t and 1 minus t. Now these tricks work, okay, but not for all integrals, because you cannot solve all integrals, right? So just for some set of integrals. So yeah, let's consider this integral here. Okay. Yeah. If you make this substitution, you have x equals t2, t divided by 1 minus t. So these are just, this is the substitution you can make, and I just did the workings already, so I don't think we should waste so much time on that. You could do this yourself. And then you just get this after the substitution. So this integral becomes this after the substitution. Okay, here is this duster. Okay, for the sake of clarity, we could do a little bit. I don't like reading slides, so let's do a little bit of work for the sake of clarity. I'm getting good with it. Okay, so you have this. Yeah, you have this integral. So what we want to show is this. We want to show that this integral is equal to this integral. Okay, if you want, okay, and these two integrals are just this. Okay, and we could add one more. Okay, so yeah, we call this Euler's second integral, or the Eulerian second integral, or Eulerian second integral. Yeah, Eulerian second integral. This would be the first one, and this would be the trigonometric one. Okay, so from here to here, you make the substitution. So from here to here, you make this substitution. T equals x over 1 plus x. From here to here, you make this substitution. T equals sine squared theta. That's just it. Okay? Okay. That does it. So, yeah. So we have these three forms. And this is just beta, alpha, comma beta. So B of alpha, comma beta, if you want. So from here to here, you make the substitution. T equals x over 1 plus x. From here to here, you make the substitution. Sine squared theta equals t. Now, you could also reverse it. From here to here, you could make the substitution. Again, t equals x over 1 plus x. You get this back. Okay? So there's nothing really There's nothing really complicated about it. So start with the beta integral. So now this is from 0, 1 to 0, infinity. The previous one is from 0, infinity to 0, 1. So if you make this substitution and you do this calculation, this is what you would have, right? Should we do it? Maybe. Okay. Yeah, so let's do it. So you have t equals this. This means t plus tx equals x. This means x minus tx equals t. This means x1 minus t equals t. X equals t divided by 1 minus t. Right? Okay, so we have 1 plus x in the denominator. You just do 1 plus x here, and you have 1 plus t divided by 1 minus t. And this is just 1 divided by 1 minus t. Okay, so now we have 1 plus x, and we have x. So we just substitute into this. Okay, if you make that substitution, okay, now at the limits, what happens at x equals infinity? So yeah, this was the substitution, right? So as x goes to infinity, what do? You could rewrite this way, right? And then as x goes to infinity, what happens? T goes to 1. Good, because this goes to 0, right? And you have 1 plus 0. Okay? And when x is 0, when x equals 0, what happens? When x equals 0, t is 0 divided by 1 plus 0, which is, ouch, 0. Okay, now we just replace the limits. So the integral at infinity is 1, and this 0. And for the x, you have t over 1 minus t, so this alpha minus 1, right? For 1, this is 1 plus x here, but now we have the reciprocal. So we just take the reciprocal and have 1 minus t alpha plus beta. And for the derivative, what do we have for the derivative? So you have x equals this. And yeah, you could try to do the derivative. If you do it, you would have 1 divided by, okay, this is it here. So we have 1 plus x equals 1 over 1 minus t. This is much more easier. When you differentiate both sides, you would have dx equals v du over dx minus u dv over dx, right? Over v squared. And this is this times 0. When you differentiate minus 1 times, when you differentiate this, you have minus 1 divided by 1 minus t squared dt. So dx is just 1 over 1 minus t squared dt. So 1 over 1 minus t squared dt. And what happens here? This would be 0 to 1, t to the alpha minus 1, 1 minus t to 1 minus alpha, okay? Because this is 1 minus, ouch. So this is 1 minus t to 1 minus alpha, because this is to the power of minus 1 here. So that's what that means. So this is 1 minus t to the power of 1 minus alpha. So we need to subtract 2 from this, right? Times, I don't like the screeching of the chalks. So 1 minus t to alpha plus beta dt. Okay? 1 minus 2 is minus 1. Okay. Okay. Okay, so yeah, so this integral would be equal to 0 to 1, t to the alpha minus 1, 1 minus t to 1 minus alpha minus 2 is, okay, let's just write it all. 1 minus alpha minus 2 plus alpha plus beta dt, right? Alpha minus alpha is 0, and 1 minus 2 is minus 1. So what do we have left? We have this. T to the alpha minus 1, 1 minus t to the beta minus 1 dt. And this is just d of alpha beta, right? That's it. So you could do from here to here with the substitution, t equals sine squared theta. Or we could just quickly follow the slides. So this is all what we just did on the board. This is everything here summarized. So now we could go from 0, 1 to 0, infinity with the same substitution. And we would end up with this. So if you see any integral of this form, what do? You just write it in the beta form. Okay? Let's play some examples. Let's play with some examples. I would write an integral, and then you would tell me the beta form. Okay. Let's play with some examples. Okay. So if you have x to the 9 divided by 1 plus x to 11. So what is alpha and what is beta?
So alpha is 10.
Okay, alpha is 10
Beta is 1.
and beta is 1. Okay, that's correct. So for this integral, what would we have? We would have b 10, comma 1. Right? Good. And what would this be? This would be what? R10, gamma, not R, but gamma, Greek. Okay, gamma of 11. Okay, and this is going to be 9 factorial divided by 10 factorial. And this is going to be 1 over 10. Right? Okay. Let's go to another form. Okay, let's quickly just brush through the slides and continue. Okay, with this, when you make t equals sine square theta, you get the b of x comma y. It's elementary, as you can see on the board, and you can also do it yourself. Now, usually integrals are just of this form, okay? You don't find them in this form. Okay, what I'm trying to say is integrals, you just find them this way. For instance, the one with pi over 2, maybe sine 7 theta, I don't know, cos 11 theta. I mean, you don't find them in these forms. 2 times sine, I don't know, 2 alpha minus 1 theta cos 2 beta minus 1 theta d theta. So it means
That's 7 times 2 alpha minus 1.
exactly. So you have like 2 alpha minus 1 equals 7. And what? 2 beta minus 1 equals 11. And then you need to, I don't know. So this is a little bit of work, right? Because this is the beta integral here. So when you make this substitution, what would happen? For instance, for this one, you would have alpha to be 4 and beta to be 6, right? So this integral would be what? Would be half, right? Half beta 4, 6. That's clear, right? But you don't find 4, 6 in the exponent. So to make life easier, I kind of reduced it here, okay? So when you have x on the power of sine and y on the power of cos. So what do? You just do this. Okay, it's a bit messy on the board. Let's make life easier. Okay. Okay, when you find that, so what do? You just do this. 0 pi over 2 sine 7 theta cos 11 theta d theta would be half b 7 plus 1 over 2, 11 plus 1 over 2. Now life is easy. Okay? Now this would be half b x plus 1 over 2, y plus 1 over 2. So when you make that substitution, you just get this. Okay? Half b x plus 1 over 2, y plus 1 over 2. Okay, summary. This is Euler's first beta integral. This is Euler's second beta integral. And this is the trigonometric beta integral. These are the 3 forms of the beta integral. All evaluate to be x comma y. Okay, you want to take a shot? Okay. Yeah, and these are examples. I mean, we've done a lot of examples. So this is one, this is another, and this is one more. Okay. I should check if this integral really converges. The third one. The third one is, yeah, could require some analytic continuation, I guess. But I didn't check it. I had it on my mind to check, but I didn't have enough time. So, okay. But yes, the other ones surely converge. Okay. These are maybe slightly complicated examples. We've been doing the ones with, integer values. How about the ones with fractional values, right? Like 3 over 2 and half. So these are the kinds of integral that Wallis couldn't do, the ones with fractional values like this, okay? Okay. Yeah, how do we do this? The same, right? You just, before we should have like, -1 here, right? So here you would have a +1, and here you would also have a +1. Okay? This is what I am saying. Okay, I want to make life easy. So I am saying this. If you have 0, 1, t to the m, 1 minus t to the n, dt, you have this b, m plus 1, n plus 1. Life is easy this way, okay? If you remember, you need to have a -1 here, then you would have an m here, to have an n minus 1 here, and you have an n, but life is easy this way. If you have this, sine alpha x cos beta y, what am I writing? X dx. This would just be half b x plus 1 over 2, no, alpha plus 1 over 2, beta plus 1 over 2. Life is easy this way, right? I mean, you don't need to, you don't need to recollect well, you need to know the usual beta form, but I think life is just very easy this way, okay? You just have this. You don't need to worry about anything else. So here you just have b, 3 over 2 plus 1, half plus 1, okay? This is another example. Okay, so to do this you need to know the half values of the beta. Now let's play with some gamma stuff. Okay, let's make use of the second board. Okay. Okay, so this is what I am saying you need to know. We proved this in the first talk. Yeah. So now we need to know something like 3 over 2, right? Yeah. Of course you know 4 over 2, that's gamma 2, which is 1 factorial. You know the integer values. But you need to know something like, 5 over 2, like 7 over 2. Now,
You can use like the recursion.
yeah, we can use that. So, if you recollect, we also proved this in the first talk, right? We proved this in the first talk. So, for 3 over 2, we just do half plus 1, which is just half gamma half by the recursion, right? And this is just half times pi. Easy peasy, right? Very easy. Okay, it's very easy. You want the gamma, 9 over 2. What do? You do gamma, what? 7, right? Which is 7 over 2. But, I mean, you could just write it 7 over 2. The next one would, okay, this is 7 over 2, right?
5 over 2.
Okay, I need to get a better chalk. So this is 7 over 2, gamma 5 over 2 plus 1 equals 7 over 2 times 5 over 2, gamma 5 over 2, right? You could just continue. 7 over 2, 5 over 2, 3 over 2. The next one would be gamma 3 over 2, 1 over 2, gamma half. It's like this. So you just multiply 753 gamma half. So what could you, or what can you observe from this?
So like we can evaluate like each half values.
Yeah, that's very nice and very impressive of you. So okay. Okay. So he was saying something really nice. He says we can evaluate gamma values of this form, right? And that's true, isn't it? So what do we have for stuff like this? Okay, you don't need to guess anything. You don't need to know anything. So for this one,
Maybe like -1,
okay, 1 minute. So for 9/2, for instance, we had, so this is 2 times 4 plus 1, right? Over 2. And what did we have for that? We had 7, 5, 3. So, okay. 7 is 2 times 4 minus 1, right? So there's something we call the double factorial, okay? Which means just keep repeating the odd values, right? Like just keep decreasing the factorials by 2. That's the meaning, right? So divided by, if you check this, you have 1, 2, 3, 4, 2 to the power of 4, which corresponds to 2 to the power of 4 here. 2 to the power of 4, right? Times root pi. So surely we can write a formula for this. You just write 2n minus 1 double factorial over 2 to the n times root pi. That does it, okay? Oh, yeah, thank you. Grazie, in Italiano. And M, grazie mille. Okay, that works. Okay, so that's it. So life becomes easy with this. And you could check with the 3, you just replace with 2 times 3 minus 1, which is 6 minus 1. Okay, now, this is 2 here, 3/2. So, yeah, so this is going to be 1. So if m is 1, you have 2 times 1 minus 1, which is 1 factorial, 1 double factorial, which is 1. So it works. So that works. So, yeah, you could just note that. I didn't put it in the slides, but you could note that. Okay? Yeah. Next example is this, okay? It also has the half values. Then you don't need to compute very much. Life's very easy. And one is, okay, the last one was chopped off, okay? The last one was chopped off. I don't know, maybe the computer, because it's very much visible on my computer. So, yeah, this is just a discussion on the beta integrand. So what do you notice? Well, as t goes to 0, what happens? This goes to 1, right? And you just have this asymptotics for the two of them. So yeah, you have this approximately t to the x minus 1 and this approximately 1 minus t to the y minus 1. So it's quite beautiful because, yeah, you have these two things, okay? And you can also notice something about this integrand, okay? Okay. I didn't put it here. Okay. 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 think the discussion I was trying to remember was the one about poles, but it doesn't really matter.
The poles.
Poles, like
Yeah,
singularities.
I know. One pole here.
Which one?
I'm Polish.
Oh, okay. Yeah, yeah, okay. That was funny.
You know
Okay.
you know the joke. What is the integral over the curve of the Western Europe?
Oh,
You know it?
no, but,
It's zero because all the poles are in Eastern Europe.
ah, I see.
It was supposed to be funny.
I'm still thinking about it. Okay, I would say, well, at x equals 0, here we have a pole, okay? But not maximum, okay? So we have a pole here. At x equals 0, then this becomes a pole, right? You have 1 over t, and as t tends to 0, you have infinity. And the same here, when y equals 0, we also have a pole, right? Because this becomes 1 over 1 minus t, and when t goes to 1, you have, you know, something, you have, yeah, infinity. So the next one is about proving that beta xy, or bxy if you want, bxy is gamma x, gamma y over gamma x plus y. You don't get it for free. You don't get it for free. So yeah, you need to prove it. And yes, so there's a proof here. The proof in this slide is the simple one. I don't think any of the proofs that I know is complicated, but yeah, this is the simpler one. The other one makes use of some infinite product and, you know, yeah, maybe not infinite product, pardon me, but it makes use of some other kind of factorial, okay? Which I did not introduce at the beginning of the course. But yeah, so we have this. Okay, we could consider this integral, this double integral. It's a simple proof. Okay, yeah, and the other proof makes use of the rising factorial. Yeah, that's the thing I was trying to remember, and we didn't discuss it. We didn't discuss it, so I just inserted Poisson's proof into the slides because they are easy to, because it is easy to know. So, well, what do? You just share the integral, bring the u things together and bring the v things together, and you just have gamma x plus y. Usually, the next thing that would come to your mind would be to do some variable change, right? So, yeah, let's do this variable change. And when you deal with variable change, you need the Jacobian, a very simple thing as well. So this is the Jacobian. It's a simple thing, the determinant of these partials, okay? Just do the partial, u with r, partial, u with t. And, well, it doesn't matter. You could have your u here, you could have the v here, you could have your u here with t and the v here because, you know, the determinant remains the same on the transpose, okay? This is what I'm saying, okay? If you do this determinant, you have t times minus r, 1 minus t, okay? And this is minus r with t, right? Minus r with t minus r plus rt. This is 0, so you have minus r. It doesn't matter if you have the determinant this way. Determinant t, 1 minus t, r minus r. It doesn't matter. You still have minus rt, okay? Okay, you still have minus rt, minus r, 1 minus t. So you have minus rt minus r plus rt, you still have minus r. So determinant remains the same on the transpose. So yeah, you could remember it in this form, basically. Okay. So yeah, you need to take the absolute value, okay? And you have plus r. So that's the required Jacobian for the variable change. So what happens? Okay. So when you make the substitution, u equals rt and v equals r times 1 minus t, this product becomes this. Yeah, when you multiply by the du dv, you get this. And that's just this. Okay? Okay, this, that, but let's give it an explanation. Okay. A little bit of an explanation. Okay, a little bit of an explanation. So, yeah, we made the substitution u equals rt, v equals r1 minus t. Remember, u is on 0 to infinity, if you want this, and v is here too. So, and we changed the variables to r and t. So when u is 0, r is 0. When u goes to infinity, r goes to infinity. Which means r becomes where? On 0 to infinity, right? And here, you have the one for v. When, yeah, we want something for t now. So let's go to, okay, we could also use this as well. So when u goes to infinity, okay? Let me see. Here we have the one for t. Okay. Yeah, what happens when u goes to infinity? Yeah. When u and v go to infinity, let me see. So you could have u divided by v equals t divided by 1 minus t, I see. And what else? Okay, surely when, okay. Okay. So when u is 0, t is 0. Now this is what I wanted. And when v is 0, you have t to be 1. Okay, that does it. So when u is 0, t is 0, and when v is 0, t is 1. That's fine. And when u goes to infinity, t goes to infinity. And when v goes to infinity, what happens? I have to be careful. Let me see this again. Okay, we could check this later, but things look a bit messy. Okay. But yes, yeah. So the integrals from 0 to infinity on both sides for u and for v becomes this here. So which is just these two products, okay? So this is a single product, which is just this product here. So we could take a moment. Maybe we could pause it here.